Good day, I'm Jed Ethan Fernandez, and I'm here with my partner Jose Enrique Guevara. In our talk, we will give a brief overview on the Marshall and Olkin family of distributions. We would first give a brief introduction to the Marshall-Olkin method, then we would look at its probability density function and hazard rate. And lastly, we would look at what happens when it is applied to the exponential distribution. To start off, we first answer the two main questions. What is the Marshall-Olkin method and why is it important? So what is the Marshall-Olkin method? In the year 1997, Albert Marshall and Ingram Olkin together published a paper on where they developed a method in extending a node distribution by adding a parameter. This method we call the Marshall-Olkin method. They proposed that if capital F bar is a survival function of a continuous random variable, then capital G bar given below is a valid survival function. Here, we would extend the distribution given by f with the parameter alpha. We have g bar of x is equal to alpha f bar of x over 1 minus alpha bar f bar of x, where x is from negative to positive infinity, alpha greater than 0, and alpha bar is equal to 1 minus alpha. And if we substitute alpha bar for 1 minus alpha, we get this next equality. Also note that if alpha is equal to 1, then we are left with the same distribution since f bar would be equal to g bar. Next, we talk about its importance. First is that standard distributions are restrictive. Standard functions like the exponential distributions have a constant hazard rate. This makes them less of a viable distribution to model real-life situations. By extending distributions, we are able to make them more flexible and a better model for real-life situations. Now, there are other ways to extend distributions, so why is the Marshall-Olkin method important? This is because all methods of extending distributions have a property called the stability property. This means that if the same method is used two or more times, we would not be able to get a new distribution, and we are left with the same distribution. So finding new methods is important since we cannot rely on the same methods to get new distributions. And with more distributions, we are able to model things more accurately. Next, we will give a brief example of the application of the Marshall-Olkin method that is very relevant in our current situation. We all know about COVID. It has affected all of our lives. It is the whole reason why we do not have face-to-face classes. Recently, on January 2022, Ihab Al-Metwali and Doa Abdo, together with their group, were able to find a new distribution using the Marshall-Olkin method. We would not go more in depth into their paper, but if you are interested, you can find their paper with this link. They were able to use the Marshall-Olkin method to create a distribution that models the daily COVID cases. Now we discuss about the probability density function of a Marshall-Olkin method. Note that the smaller letters are the PDF of the capital letter, and the capital letter is a cumulative distribution function, and the capital letter bar is a survival function. So Marshall-Olkin said that the PDF of the new distribution G is alpha times the PDF of F divided by the square of 1 minus alpha bar times the survival function of F. Now we are going to derive this. First, we note that the PDF is the derivative of the CDF, and the CDF is 1 minus the survival function. Next, from the Marshall-Olkin method, we substitute capital G bar. Then, we substitute alpha bar with 1 minus alpha and f bar with 1 minus f, and we combine the two fractions. Terms will cancel out and we'll be left with this equation. Next, we get the derivative using the quotient rule, then express in terms of f bar and alpha bar, and we are left with this final function, which is equal to the PDF that Marshall-Olkin suggested. Next, we go on to the hazard rate. This part is more simple. The hazard rate R is given by the following. First, we recall that the hazard rate of a distribution is the PDF divided by the survival function. This could easily be derived from the following, where h of x is also the hazard rate of the distribution given by the function f.
So now we try to introduce a new parameter to the previously discussed equations. The first equation to be discussed is g bar of x given alpha. Lambda can be used as a second parameter simply by equating f bar of x to be equal to e raised to negative lambda of x. Using our previously discussed g bar of x, we now have g bar of x given alpha and lambda to be equal to 1 over e raised to lambda x minus alpha bar. With the same constrictions, being x is greater than 0, alpha is greater than 0. Our new parameter lambda also has the same constriction being greater than 0. By creating a new function given new parameters, we can now try to explore how this distribution behaves. So the first case we would be using is alpha is equal to 1. When alpha is equal to 1, we now have alpha bar is equal to 0. Equating alpha bar into 0, we get the new function to be equal to 1 over e raised to lambda x. It can be seen through previous lessons that this has the structure of an exponential distribution, and thus properties of an exponential distribution will take into effect into this case. Using the same technique of adding a new parameter, being f bar of x is equal to e raised to negative lambda of x, thus including the new parameter lambda, we can now do this to the density function and the hazard function. So here is the newly created density function given the new parameter lambda. The second equation is the raw equation created when we equate f bar of x to be equal to e raised to negative lambda x. The final or the first equation seen here can be derived from the second equation simply by multiplying the right-hand side by 1 or an exponential function over an exponential function. Similarly, we can do this with the hazard function, and we now have the hazard with a new parameter. So this is the intention of this study. By creating a new parameter to the previously created distribution, we now have a distribution that is not constricted to only one parameter. It can be seen through our intro that what is lacking in most of the distributions now is that it is too constricted. This can be less constricted simply by adding more distributions. Through the technique that we used in adding or implementing a new parameter, we can now make a distribution that will be less restrictive, thus being able to be used in worldly problems such as the COVID cases and some other recently explored cases. It can be seen that in our intro that COVID has a lot of parameters required, and it is not enough that we use old distributions, but it's also not enough that we try to create new distributions since these are not easily created. What can be done through this study is to use old equations, old distributions, and implement new parameters into it. When we have a new distribution with new parameters, we can now discuss how it is behaved given several cases. And now we can see that this can be used